Hello, everyone. Welcome back. Today, we are going to be talking about acid-base chemistry. And so, this is the point in the course that I will say things are going to start ramping up in terms of difficulty because everything up to this point has been very much so partially memorization, partially just going through and getting the basics down. Now, we're going to start applying everything. And where we start applying everything is here in acid-base chemistry. So you may have noticed the acid-base chemistry. We do have multiple lectures planned on this. It is because it is a very broad and important topic for us to talk about, and it will follow you throughout all of OChem 1 and OChem 2, just like resonance did. And so to begin our journey through acid-base chemistry, the first thing we have to do is talk about our definitions of acid-base chemistry. And there are three of them that we're going to be looking at throughout this course. The first one is what I will say is the most useless one. You just need to know it exists because it's the one that you guys probably know well. And then we'll go through the other two that are much more important. So the first one here is Arrhenius acids and bases. And essentially what the Arrhenius definition states is that acids increase the concentration of H3O plus in water. So you can think of this as, here's a good example of it. If you were to throw HCl into a bucket of water, what you're going to end up seeing is that, oh, hey, upon this reaction occurring, you'll end up with H3O plus along with Cl minus. Right? And so this would be a good way to think of the Arrhenius acid base because as you can see here, the product is H3O plus. If we're making H3O plus, that is an Arrhenius acid. The next definition for Arrhenius that we care about is bases, and this one is also very simple. Bases increase the concentration of hydroxide in water. So for this, there are multiple ways to think about it, but the first way that we can say is if you throw sodium hydroxide into some water, as we know from good old general chemistry, hopefully, this will split up and the salt will dissociate into sodium hydroxide itself, and the water will just be around as water. But as we can see, the Arrhenius definition is here because the product here is hydroxide, and so it is increasing the concentration of hydroxide in water. So this is a very rudimentary way to think about ABC. And so this whole chunk here is very simple, right? It is an extremely simple way to think about acid-base chemistry, and thus we don't use it. All right, it's just not useful because it's too rudimentary. So in reality, we are primarily going to be using the second and third definition of acid-base chemistry, and the second one is our good friend Bronsted-Lowry. And Bronsted-Lowry gives us a much broader definition that is the primary good definition that we're going to use for a lot of our acid-base chemistry itself. And the first one is about acids. And acids, simply for Bronsted-Lowry, they donate protons. All right. And so protons are a hydrogen with a positive charge. Right. And so essentially, these H pluses come from these acids. And so if we recontextualize our previous example with HCl, we can imagine, right, if we have this hydrogen from HCl, toss this into some water, we're going to see the same reaction as above. But our H3O this time, we can rewrite it as such, right? So we can see that the proton from the HCl is now attached to the water. It's made H3O plus and still Cl minus. So essentially for Bronsted-Lowry, if they donate protons, you're just looking for where that proton, that hydrogen, has been transferred. All right. For Bronsted-Lowry bases, it's very easy to understand because they accept protons. So we can once again look at that very simple thing that we drew up top for our Arrhenius definition. And we can say, all right, what if we colored the hydroxide here? So sodium hydroxide in water. Well, one of the things that can happen here is rather than it just being the sodium and the hydroxide that break up, what if we're saying that the sodium's here, we've made hydroxide, and one of the hydrogens from the water was actually taken by the basic hydroxide we started with, right? So this would be a definition of a Bronsted-Lowry base. They accept protons. All right, we're going to dive deeper into Bronsted-Lowry in just a second, but let's get to our third definition of acids and bases, and that is Lewis acids and bases. Now, this is, some would say, even more important than Bronsted-Lowry, because Bronsted-Lowry we're going to be looking at a lot for acid-base chemistry, but Lewis is the entirety of the organic chemistry idea of how electrons flow, right? And so looking at this, Lewis acids accept electron pairs, right? Whereas Lewis bases donate electron pairs. And so we can look at this in a larger example reaction because this one's going to take a little bit more drawing. And so we'll take a look once again at our very favorite HCl and water example. So if we're looking at water with HCl, we got to ask ourselves, what is actually happening? Well, we know in the end, based on what we saw for our Bronsted definition, we end up with this oxygen-hydrogen bond that's end up formed, and then we have this chloride ion with that negative charge. So what we're actually seeing is the oxygen from the H2O is giving electrons to the hydrogen, right? And then that hydrogen is breaking the bond with the chlorine, and it is giving the chlorine those electrons. And the end result is that we do have what's shown over there on the right. And so we can imagine, given this definition, that the hydrogen here, right, we can see it taking an electron pair from the oxygen. So the hydrogen here is the Lewis acid, as it is accepting the electron pair from the oxygen, right? That inversely, we can point at the oxygen of the water and say that here, oxygen is the Lewis base because it is giving its electrons to the hydrogen, okay, to that proton. And so with this, it sets up a very important idea that we actually have to follow up with, okay? And that is these arrows over here. So we've already looked at electron flow arrows for resonance, but let's take a look at electron flow for reactions because it's a little different than what we saw for resonance. So up top, right, what we see happening, we're going to make this into a little bit of a more useful picture by actually showing the lone pairs between some of these atoms. So what we showed up top was that the electrons from the oxygen are coming to the hydrogen, and the electrons from that bond are going to the chlorine. So what these arrows actually mean, it's the same as we saw before, right? Where on the left-hand side, well, I guess on whatever side the arrow is not pointing to, this is where the electrons are coming from. And then on the right-hand side is where the electrons end or end up. And now this is the same definition that we gave for resonance. But the thing is, with resonance, since it was in the same molecule, there was nothing really super special going on. But the thing is, there's a tie between where the electrons come from and where the electrons end up. And that is the fact that most of the time this will form or break a bond. right? And that's exactly what happens because if we look over here at what the products end up being, right, if we draw them in a similar orientation, where those electrons were on the oxygen, there is now another hydrogen there. And then the chlorine, which gained that lone pair, right, we can draw it where up here, rather than just having that arrow there, we can draw the rest of the lone pairs on the chlorine, and it should be very obvious from here that the chlorine now is just chilling out with all eight of those electrons, which gives it a negative charge. Now, of course, the oxygen, that set of electrons, is now in this bond between it and the hydrogen, which essentially means now it is positively charged. So whenever we're drawing these electron flow arrows from now on, it is a lot to do with breaking and forming bonds, right? Wherever the electrons are coming from, it's pretty much saying, I want to form a bond with that thing, right? So in this case, the oxygen says, I want to form a bond with the hydrogen. And then the fact that we have electrons leaving the bond between the hydrogen and the chlorine and going to the chlorine, it is saying that this bond is being broken and the electrons are going to the chlorine. Hopefully that makes sense because we're going to be seeing a lot more of it. All right. So with that being said, let's dive into Bronsted-Lowry reactions. So looking at these, the first thing that we want to do is we want to define some of the pieces that we have here. And to do this, we're going to look at the exact same reaction. I know it's a very boring reaction and we keep seeing it, but I do want to make sure that we are well aware of each piece of the puzzle here, because that is going to help us define everything for the rest of our acid-base chemistry chapter. So these were the same products, just drawn out with very explicit bonds. And as we saw before, the oxygen's grabbing that proton, and we're giving the electrons to that chlorine. Now then, we need to give some definitions for what these things are. And the first thing that we can define is that the HCl here, which we already know is hydrochloric acid, it is an acid based on Bronsted-Lowry definition, right? Because based on Bronsted-Lowry definition, it just has to give away a proton. In this case, it is giving away a proton to the water. That being said, the water in this case is then a base, because remember that bases accept protons, which is exactly what that water is doing. It is accepting a proton. Now, what you need to know in terms of definitions is that your base and the product will become what is called your conjugate acid. And the reason it's called your conjugate acid is because upon becoming protonated, upon grabbing that proton, it is now more acidic than it was. So it is a conjugate acid. At the same time, the acid on this side becomes the conjugate base on the other side of the reaction. And so what this means is if we were to put this reaction in the reverse direction, the H3O plus would be our acid and the Cl minus would be our base. Okay? And so these definitions are really important because knowing what your conjugate acid and conjugate base are will help you kind of determine which way reaction should go. And then it also helps you determine which way equilibrium is going to go, which we will look at a little later on. But the first thing that we got to think about is how do we actually determine what an acid is? And the way we do this is we're going to go into next lecture what makes an acidic proton. But the first thing that we can do is we can define what many acids are. And what many of them are is some type of proton attached to your acid, and it usually has a positive charge. That way, upon deprotonation, right, there's your H plus, you'll end up with a neutral species, right? So this would be your acid, and this would be your conjugate base. So the first thing that we want to think about is, does it have a positive charge? If yes, it's probably an acid. Same idea goes for a base, right? If we have a base that has a negative charge, right, like this one here, upon becoming protonated, right, upon gaining that proton, it will be neutral. So this would be your base. This would be your conjugate acid. And so with this, we can say that a negative charge thing is very basic, right? It has electrons to give up. And so those are two good ways to identify if something is an acid or a base. And again, next lecture we'll go into more ideas behind what makes something acidic and what makes something basic. All right. But looking at this, we can apply this to multiple different types of reactions. And so with that, we'll bring up another one and we'll try and identify what the acid and base is within this reaction here. So, looking on this side of the reaction, right, we have two species. So one is clearly going to be an acid, one's going to be a base. And we just have to ask ourselves which is which. And at the moment, we don't see any charges, right? So we have to look a little deeper. And you notice that over here on this structure, it's a sodium ion with a hydrogen. And so if we think back to ionic bonding, right, ionic bonding happens a lot between metals and other things. And sodium happens to be a metal. And if you're seeing a sodium metal being present, this is not exactly sodium metal. Instead, since it's bound to this hydrogen, it is a sodium cation. And so what we're really looking at here, the actual structure of this, is it's sodium plus H minus. And the thing about a lot of these cations here is that these are spectator ions. And if it's a spectator ion, that means that it does nothing. And I'm going to put that in quotes because it's not entirely true that it does nothing. It's just not going to do anything important for the sake of this course for us. So just an idea of a couple spectator ions that you'll see a lot throughout this course. Of course, we have sodium, we have potassium. That one's also classic. Calcium can appear, but it is a 2 plus metal, so it'll be a little different. And then another one that you might see often is cesium plus. And you'll notice that one thing is true amongst all of these, and that is since they are metals, they're in the first two columns of the periodic table. So you'll want to keep an eye out for these because they're going to be the things that kind of tell you when something is a base, right? So looking at this, we now have a good definition, right? We know that this hydrogen with a negative charge, this is going to be our base. All right, so what's that base going to do? Let's take a look back up at the top of the reaction here. It is going to look for an acid. And this must be our acid because it can't be anything else. And in this case, we see that it has a nice hydrogen sitting there on the oxygen. Now, you may be thinking there's other hydrogens on this molecule. That is true. We're not going to worry about those right now. We'll worry about them next time. For right now, all we're going to worry about is if the hydrogen comes down here, it can grab that proton and it can give the electrons to that oxygen. Okay? And that is going to give us this oxygen, which it originally had two lone pairs on it, but now it just gained another one. And an oxygen with three lone pairs and one bond, if you did formal charge, that is negative. Now keep in mind, our sodium does still exist over on this side of the equation. It just does nothing between the two, so it's still just Na plus. And then we see that the hydrogen that had a negative charge grabbed a proton, right? So that proton has no electrons around it. It's just a hydrogen, which means that it formed a bond with that guy, and now they're both neutral. And we can label these now because our acid, which was the thing with the OH, is now the O minus, which means this is our conjugate base. And then the hydrogen-hydrogen bond that just got formed, this makes our conjugate acid. Okay? So the main idea that we're looking through during a lot of this acid-base chemistry is you want to identify your acid, you want to identify your base, and you want to ask yourself what the product is going to look like. Okay? So that's a good example. Let's do another one, right? Let's look at something along the lines of this here. So we'll do, no, yeah, we'll do this. So looking at the structure here, right, we're asking ourselves which is the acid and which is the base. On the left-hand side, we see that there is a K, right? That is potassium. And based on what we had just said, that tells us that the potassium is actually going to be a spectator, right? Because this must be an O minus, right? It takes all of the electrons there, and then it's a K plus. We see that has a negative charge. That must mean that this is our base. While on the other hand, this HI is our acid. Now, you all might be noticing that some acids are pretty easy to identify if they're strong acids that you remember from Gen Chem. And we'll talk about those a little more in just a second. Either way, we have our base, we have our acid. So we know that the base, that oxygen with a negative charge, is going to come up and it's going to grab that proton. And then the HI bond is going to break and the electrons are going to be given to that iodine. So now we have that new OH bond that got formed. And while oxygen did have three lone pairs before, now it only has two. So that's a neutral formal charge. And then our product has the iodide with the negative charge. And of course, that potassium that did nothing throughout is just chilling there. And so based on this, our base has now become our conjugate acid here. And then our acid has now become our conjugate base right here. Great. Let's do another one. Examples are good, so we're just going to keep doing them as we go. So for this one, we've got this here, and then we have a structure that looks like this. So this one's a little weird, but it's very similar to what we've been talking about. We see we have a positive charge in this structure here. That should immediately alert us that this is indeed an acid. Whereas the structure over here, it must be a base. But whenever we're looking at this base, we have to think to ourselves, where are the electrons coming from? Right? Many of the others we've been looking at have all had negative charges. This one does not. It's neutral. Well, the electrons have to come from lone pairs, and the only lone pairs available are on the oxygen. So that means that the base is going to use the electrons from the oxygen to come over, grab the proton, and give the electrons back to the oxygen on the acid. And what that's going to do is now it's just going to be an OH. It's going to be neutral. But when that base took the proton, right, it used one of its lone pairs to do so. Now it has a positive charge. And we can once again label this is going to be our, oh, whoops. This is our conjugate base because it came from our acid. This is our conjugate acid because it came from our base. So hopefully these are starting to make a bit of sense, right? Let's do one more where we start from two neutral species like we were before with the HCl and water. But we're going to do this one with something that you all may be a little less familiar with. So, looking at this, right? If we look at this structure over here on the left, we see that it's got a sulfur, a bunch of oxygens, a couple hydrogens present. And then on the right, we have this nitrogen and a bunch of carbon-hydrogen bonds. And this is an example of where we have two neutral species, but they're clearly going to end up making charges in the end. All right? So the question is, which is our acid and which is our base? Well, for those who remember your strong acids, this over here is a strong acid, right? It is sulfuric acid, it's H2SO4, so we know without a doubt that is going to have to be an acid. That means that this structure here must be our base. So looking at this reaction, we would say that the electrons from the nitrogen are going to come over, grab one of those protons, give the electrons to the oxygen, and we're going to end up with the negatively charged oxygen because we just gave it another lone pair, and then the nitrogen is going to then be positively charged because it just gained a proton. And so this, of course, is our conjugate acid, and the sulfate ion is our conjugate base. But more importantly, it brings up an interesting point, and that is that you also need to know your strong acids. All right, so we're going to take a second to list those so that you can remember because it's useful to know them, right? Knowing when something's going to act as an acid is a really good thing. And so our strong acids are H2SO4, right? Sulfuric acid, HNO3, that is nitric acid. You have all the halogen acids, right? Hydrochloric, hydrobromic, and hydroiodic, right? Those are all strong acid. And then H3O plus is also technically a strong acid. Now, that being said, you'll notice that fluorine isn't shown in the strong acids. That is because it is relatively weak. All right, so keep in mind if you ever see HF, don't necessarily treat it as a strong acid. It will only act as an acid. It is just not strong. Okay, now let's take a look at the next piece of information that we need to pay attention to when we're looking at these Bronsted-Lowry reactions, and that is this idea of charge balancing. So for charge balancing, the idea is that whatever is in the products for charge should be the same as what's in the starting material for charge. So if we take a look at something like this reaction between HBr and diethyl ether, right? We know HBr is a strong acid, so it must be our acid, which means that this over here is our base. And we know from our previous examples we've talked about that it must be the lone pair electrons on the oxygen that act as our basic lone pair. It'll come over, it'll grab that proton, give the electrons to the bromine, and that will generate this Br minus, and the oxygen will have a proton with a positive charge. Now, as long as you've been paying attention to all of your formal charges, you should never get it wrong on this side. But you should always double check. And how you do so is you're going to look at the entire left-hand side over here. And based on looking at this, you should be able to see that there is no charge over here. So this side is neutral, right? Zero charge. On the right-hand side, we can say something very similar because we have a positive and a negative, which if you do +1 and -1, that equals 0. So this is also neutral. It would be incorrect if you were to have an additional charge over here that makes it not neutral. All right. The same is true if we were to say take a reaction such as this, OH minus, HCl, right? We know that hydroxide is very basic, so this is going to be our base, and we know HCl is a good acid, so that'll be our acid. So the oxygen lone pair electrons will grab that proton, will break the bond, give some electrons to the chlorine. That will generate water, right, which is just H2O, along with Cl minus. And again, if you were doing your formal charges correctly, this should never be a problem. But you can also double check yourself because over here we see that there's a negative charge. So this is a -1 charge overall on that side of the equation. And then over here we see the chlorine has a minus charge. So this is also -1 charge. If you had ever ended up in a situation where there were more charges in the product than the reactant, or vice versa, you would know that it's incorrect. So make sure that whenever you're drawing out these reactions, you are comfortable with the charge balancing. Okay? So now that we've gotten through that, the first thing that I want to make sure everyone is well aware of is you need to start understanding what an acid and a base looks like, right? That is what we talked about all throughout up here. It's very important because we will start asking you to predict some of the products of these reactions. All right. The next thing that we need to start worrying about is equilibrium. So this is why I say we're going to start getting into the big leagues whenever it comes to acid-base chemistry. It's because we're moving out of the realm of just being able to sort of memorize things and float along. We are now to where we need to start applying concepts. And the first concept we need to apply is equilibrium. All right. So we're going to go through equilibrium and I'm going to explain everything that you need to understand for it. And then we're going to talk about what it means in terms of acid-base chemistry, where will we be using it, and how that looks in terms of energy, which is the most important thing that we'll be talking about here in OChem overall. So let's take a look back at that good old reaction that we had seen many times before. Water and HCl is going to make H3O plus and Cl minus. All right, so we need to define a couple things. The first one is everything on the left-hand side of the arrow, these are reactants, right? Those are the things that we're putting into the reaction. The things that come out are on the right side here. These are products, okay? And in between, this is also very important. These set of arrows are different from what we've been using before. Everything that we've drawn up to this point have been resonance arrows. But this whole presentation, you'll notice I haven't been drawing resonance arrows. I have been drawing these, which are equilibrium arrows. And so these are reaction arrows that are primarily meant to show that the reaction can go forward or backward. I will say right now that if you draw equilibrium arrows for every single reaction, you will never be wrong because every reaction is an equilibrium. So we will be stating every reaction as an equilibrium for this class. All right. But keep in mind this is different from resonance arrows, right? These equilibrium arrows are this back and forth. That is not the same as the resonance arrow, which is a single arrow with two arrowheads, right? So the one on the left is our equilibrium. The one on the right is resonance. Now, the reason I make this distinction is because if you draw an equilibrium arrow when you're supposed to be drawing resonance, you will be incorrect. And if you draw a resonance arrow when you're supposed to be drawing equilibrium, you will also be incorrect. So what is equilibrium? Equilibrium is just a state in which a reaction is proceeding in both the forward and backward direction, and it should reach a point where everything is balanced in terms of where the reaction wants to be. And we define equilibrium through constants. All right? So equilibrium is defined by these constants. And you've seen these constants before, right? The equilibrium constant is KEQ. And if you're thinking back to your good old Gen Chem time, KEQ was equal to the concentration of products over the concentration of reactants. All right? If we wanted to make this a more appropriate one for the reaction above, we could state that KEQ is equal to the concentration of H3O plus and the concentration of chloride, Cl minus. That would be over the concentration of water and the concentration of HCl. And what you can imagine in terms of equilibrium is this KEQ constant tells us how much of the reactants have been converted into products. That is essentially what it's telling us. And so what this means is if more products are being formed, there should be less reactants, right? Because reactants are used in order to form these products. All right. The opposite could also be true. because remember, these are reactions are going back and forth. We could have more reactants and less products, which is also a possibility. And so what this all boils down to is that there are three different equilibrium constant ranges that we can be in, and it gives us different sets of ideas as to what's happening. The first one that we'll talk about is if your KEQ is greater than 1. So thinking about this in terms of the equation, for a ratio to be greater than 1, the numerator, which would be in this case the products, has to be greater than the denominator, right? Because if you had something like 4 over 4, that would be equal to 1. If you had something like 5 over 4, that is greater than 1. And so what that means is if there's more products than reactants, the products must be favored, right? The opposite is true if your KEQ is less than 1, right? A good example of this would be if you had one concentration for your products and then your concentration of reactants was 2, right? That would be 1 over 2, which is 1/2, less than 1. That would tell us that if there's more reactants than products, the reactants are favored. All right? The last type of equilibrium we can have is right in the middle where our KEQ is equal to 1. If our KEQ is equal to 1, the concentration of our products is equal to the concentration of our reactants. And what that tells us is that this would be a perfect equilibrium where no side is favored. All right? And to put that in terms of concentrations, right, because we can make these definitions a little more visual with our reaction. For KEQ is greater than 1, like we said before, concentration of products is greater than concentration of reactants. KEQ less than 1, concentration of reactants, sorry about that, is greater than the concentration of products. And then for our KEQ equal to 1, the concentration of product and reactant are entirely equal. All right. So, why does this actually matter? Because equilibrium is the main driving force of all of chemistry, right? Everything's in equilibrium, and we need to know which direction equilibrium are going or equilibria are going to go because it tells us what is actually going to happen in a reaction. So with that being said, we're going to once again draw out our favorite reaction from this lecture, and we're going to take a look at what the equilibrium says about this reaction. So people have actually calculated the equilibrium constant for this reaction, and they have found that, I'll put it above the arrow for us here, the KEQ is equal to 10 to the fifth. So that is 1 with 5 zeros after it, essentially. And so what that means is our KEQ is very, very much above 1, right? It is incredibly high. So it's 10,000, right? 10,000 is a lot. And so what that means is that there are 10,000 times more products than there are reactants, which means that this product side is very favored. Okay? Now, why is the product side favored though? That is what we actually care about. And so this is why we've been using some terms throughout this lecture that are really important. And the first one is the term strong. We used it for the strong acids. So the question is, what does strong actually mean for us? Well, strong is the same term as reactive, right? We can treat them the same when we're talking about these subjects. It is also the same as the term for unstable. So anytime that I say something is a strong acid, I'm telling you that it is an unstable acid. If I say something is a strong base, it is a unstable base or a reactive base. Now, what that means is that on the opposite side of things, we have weak, right? A weak base or a weak acid is unreactive. But it is also the most important word in all of organic chemistry. It is stable. And why is the word stable so important? It is because stability is everything. Which sounds like an absolutely weird statement to say, but it is important because stability is the driving force whenever we're looking at everything in OChem, and it's primarily related to energy. But the first thing that I want to take a look at is that favorability is related to stability. So looking back up at this reaction right here, we said that HCl is a strong, or as we like to say, unstable acid. And it makes Cl minus, which is a weak and stable base. So that's telling us that in this reaction, it's pointing towards the right-hand side because we're moving from something that is very unstable to something that is stable. Stability is everything. So, how do we understand stability? Well, to understand stability, we need to understand the statement energy is opposite of stability, right? And so what this means is if something is high energy, it is unstable. If something is low energy, it is stable. And so what we're always shooting for is lowest energy is best. So let's take a look at this reaction in terms of energy. All right. We have these diagrams called reaction coordinate diagrams, right? So this is going to be your introduction to reaction coordinate, whoops, diagrams. And what these things do is they show us energy on the y-axis in relation to reaction progress. So how is our energy changing over time? All right. So let's take a look at what our reaction is that we've been looking at this entire time, that HCl and H2O. So we know based on what we were just talking about that HCl is a strong acid. It is very unstable. And so our reactant side, even though it starts with H2O, which is a relatively stable water molecule, it's still high in energy because we have this unstable HCl chilling out on this side. In all reaction coordinate diagrams, we're going to proceed with the reaction and we're going to end up at a different energy at the very end. For this one, we know, based on what we've been talking about this entire time, that H3O plus and Cl minus are lower energy than our starting material. All right. And this is just because of what we've told you so far. We're going to give you the full reasoning why next lecture, but from what we've told you so far, we just know that chlorine is a stable, unreactive, weak base. And so what's going to happen is there's going to be this curve that comes between these things, right? It's going to go up a little bit and then it's going to go down. And the thing is, for this reaction coordinate diagram, there's a lot that we can gain from this. All right. The first is that looking at our starting and ending energies, right? Our reactant energy is greater than our product energy. This is the definition of an exothermic reaction, right? Because when we think of exothermic, we think that it releases energy, right? So a blast from the past from Gen Chem. If something goes down in energy, the energy has to go somewhere, right? And that is going to be, it's going to get fed into the surroundings. So this area right here, this is our delta H, right? And so we know that if this energy is being released, right, it's leaving the system, it is exothermic. The other thing this tells us with all exothermic reactions is that the KEQ is greater than 1, right? Because if our products are lower in energy, that means they're going to be more favored. So that means our KEQ is greater than 1. And we knew that our KEQ was greater than 1 beforehand because we had already talked about it up here. It is 10 to the fifth. All right. So anytime you see exothermic, think that KEQ greater than 1 is also the same as saying something is exothermic. All right. This is all related to something we call thermodynamics. And thermodynamics is just looking at how does energy change between two things? Is energy being absorbed into the system, which would be endothermic, or is energy being pushed out of the system, like we see here, which is exothermic? We also have kinetic parameters, and kinetic parameters are talking about speed. And so we have another piece right here, which is between where our starting reactants are and the top of the peak of the graph. And this is our activation energy, or our EA, right? So EA, oh, whoops, that's EQ, is activation energy. And what this is it's pretty much saying how much energy do you have to put in to get the ball rolling? And this is very variable. Okay. So at the moment, you don't have to worry about it, but it will come into play a little bit later. Same thing with the last little piece of the puzzle here, which is at the top of this, we have that little symbol there. This is a transition state. And again, right now, you don't have to worry about transition states. You will have to worry about them later. Right now, we are mainly focused on how is KEQ related to this graph. All right. Now then, let's take a look at another reaction coordinate diagram that's going to explain a different type of process. And I'll draw out the reaction up top here so that we have a little bit of a good idea of what we're trying to do. So let's say that we started out with oops, NO3 minus, and we toss in ethanol. Right? What is that going to make for us? Well, clearly we have a negative charge. That means that this guy must be our base. We know that that means this is our acid. We see it has a hydrogen attached to that oxygen. So what's actually going to happen is we would have to draw this out fully, but you're going to end up with HNO3 and the negatively charged ethanol. And I'll tell you right now that the KEQ for this reaction is far less than 1. How do I know that? Well, we've formed a strong, unstable acid, right? HNO3 nitric acid is a strong acid, which means that this base over here is a stable, weak base. So, taking a look at this in terms of our energy and reaction progress, whoops, sorry about that. We start out at a much lower energy, right? This is where NO3 and ethanol are currently at. And we end up generating this strong acid, which is much higher in energy, right? HNO3, and then we have this oxygen with a negative charge. So this is an example of something that has a KEQ, like we said, of less than 1, because it's going up in energy. And that tells us that the reactants are more stable, but also this is endothermic. And we know this because looking at where this material starts from and where it ends, right, we have this gap here, which is our delta H. And what that's showing is that we need to add energy, right? Because we're going up that y-axis. We have to add energy to make the product. If we have to add energy into a system, it is endothermic. All right. So, with that being said, this equilibrium process is what really drives everything that we're going to be doing throughout OChem 1 from now on. Right? We're going to have to start thinking of things in terms of energy, right? Thinking about which direction is this reaction going to go? Because looking at this one here, we know the reaction is not going to go towards the products. At least not unless we give it a lot of energy to do so. Versus this one right here, where we're using HCl and H2O, it is going to make products because it's spontaneous. All right? And then we're going to get to the point where during our quizzes and our exam, we're going to start analyzing new acid-base reactions that we've never seen before, and we're going to start asking ourselves what the equilibrium looks like. Okay? So with that being said, hopefully from this lecture you were able to take a little bit away from how acid-base chemistry works for our Bronsted acid-base chemistry, how it relates to equilibrium, and then next time we're going to jump into how to find whether or not something is acidic, whether or not something is basic, rather than just using these rudimentary rules. And from there, we'll continue down this path. We'll do a little bit of Lewis acid-base chemistry, and from there, hopefully, we'll reach a point where you'll know all of acid-base chemistry. See you next time.